So hi, everyone. Thank you for registering for this electric boilers webinar. Today, we've invited Jordan Kearns, founder and CEO of Medley Thermal, to discuss dynamic electrification as a solution for reducing boiler energy costs and emissions. So if you have any questions as we go, please feel free to send them in the chat and we will get to them during our question period following the presentation. So Jordan, thanks for being here with us today and feel free to get started whenever you're ready.
Thanks, Sierra, and thank everyone for making the time to be here during the lunch hour. I do appreciate it, and thank you for OGVG for hosting this and putting this on. As Sierra mentioned, I'm Jordan. I am the founder and CEO of Medley Thermal. So Medley Thermal exists to link clean, cheap power to thermal systems. We provide a project solution that hybridizes boiler systems to switch between electric and gas to reduce energy costs and reduce emissions. So I'll go into our solution and explain what we've been doing with other industries in Ontario and what we're interested in providing for the greenhouse sector as well. But as sort of an outline for what I'd like to go through over the next 40 minutes or so, just talk about the challenge of electrification of thermal loads in general, the problems and opportunities there. And then separate from what we're doing, just as a bit of backdrop on the energy scene, I'd like to go into the economics of electric power in Ontario and also briefly touch on the federal carbon tax increase and the impacts for growers in Ontario. Those will both just be useful background for why our projects have value, but hopefully even if our project isn't something that applies to you, something that will help you just be of interest and a learning to you in general. I'll then give an overview of our solution and our offering. And I'll then jump into a case study that we were for a project that we're currently putting together, actually in northern Vermont. We're a US-based company working in a few hubs in the US, but recently started working in Ontario as well. So with that, electrification of thermal loads. Obviously, big push globally for decarbonization. And if you look, these are US-based numbers, but Canada is very similar. If you look at energy end uses, they roughly break out into three categories. Typically, you have things that are using electricity already, and there's a big push to decarbonize the electricity sector by preserving existing nuclear and hydro and adding wind, solar, renewable natural gas, et cetera. Transportation, and there's a big push by Tesla and others to electrify the transportation sector to decarbonize that. But about a third of energy end uses are thermal end uses, most of that being large thermal uses by large commercial, industrial, and agricultural facilities like you guys. And the thermal part is probably the trickiest part to decarbonize because the economics there are a little bit tighter than even renewables for electricity or electrification of vehicles. Gasoline is much more expensive per unit energy than the natural gas. And recently, actually a few years ago, the National Renewable Energy Laboratory in the United States took a look at electrifying large boiler loads specifically. I took their study and I adapted the numbers to try to reflect, at least as of last year, natural gas and electricity prices in Ontario. And the conclusions that they come to are basically the same, though the numbers are a bit different. They looked at, on the right side of this table, you have the cost of using a natural gas boiler to generate useful heat for your facility. They say, okay, your gas input price is about $8.80 per million BTU. You burn that in a boiler at about 80% efficiency, so you have an effective cost of heat of about $11 per million BTU of delivered heat in your system. All right, so that's your status quo. If you switch over and look at electricity in Ontario, if you put that and convert it from, kilowatt hour terms, put it on common basis with the gas. So if you look at it on a dollar per million BTU basis, you're essentially paying $32 per million BTU. Now, your electric boiler, that's a cheaper piece of equipment than the gas boiler. It's much simpler, lower capital costs. It's also more efficient. It's about 99% efficient as opposed to 80% efficient. But that still leaves you with an effective cost of about 3 times that of the natural gas boiler. You're paying about $33 per million BTU of hot water or steam delivered as opposed to $11. And what the National Renewable Energy Laboratory, their conclusion was that, yeah, even though the boiler has a lower capital cost and is more energy efficient, electricity is about 3 times as expensive as natural gas on an energy basis. It will be very hard to convince people that they should switch from natural gas to electricity. And even if we could convince them, very hard on their bottom line as businesses that need to be profitable to operate, if they're going to have to start paying 3 times as much to heat their facilities or run their thermal processes. And this study, I think, is exactly right, except it leaves out one major opportunity. And that is it neglects the temporal variability of electricity costs. And what I mean by that is the price of electricity and the price of delivery charges, demand charges, all of that is highly variable based on how you consume, when you consume, and how well that behaves with the rest of your loads and the rest of the grid. So with that, I want to go into a little bit more of the economics of electric power, specifically in Ontario. And I want to open that up by saying Ontario, paradoxically, has some of the most and least expensive electricity in North America. I'm sure you guys are familiar with the most expensive. Obviously, power prices on average are quite high. But if you look a bit deeper, what you see is that those costs are really concentrated in a few peak hours. So what I've drawn here is what's called a price duration curve in the power industry. Basically, what that means is if you look on that horizontal axis and go up, that line shows the percentage of time prices are at or above a certain price. And if you look at the very far left of the chart, what you see is it really just starts to go vertical. And actually, I've cut it off here. It goes up far higher than this, but to make it legible, I had to cut it off. And this is specifically for a tariff in Electra service area, a little bit outside of Toronto, but overall, this trend is pretty similar across the load serving entities or electric utilities within Ontario. And what you can see from this is if you crunch the numbers, if you had a load that you ran flat out year round, 20% of the power costs, 80% of the power costs would be concentrated in just 20% of the time. So 20% of the hours of a year constitute 80% of the cost of running that equipment. The sort of converse of that, if you look at it the other way, is if you were to only electrify the bottom 80% of hours, your electricity cost is actually quite low, on average about 20 to 25% of the average rate. That horizontal dash line I've drawn here is the natural gas equivalent price, this time shown in electric units, just to put those on a common basis. But again, the end result of this is 80% of the time in Ontario, despite having very high prices on average, 80% of the time, electricity is actually a cheaper resource than natural gas. And this is actually based on prices from about a year or two ago. And as I'm sure you guys are aware, natural gas prices have been going up. And as we'll touch on later, there's going to be additional carbon price that will also put upward pressure on those prices. A bit of background as to why this is the case. So this is what United States and most European countries look like in terms of their energy cost breakdown. You have the energy commodity, which is about 40% of your bill. You then have what's called a capacity charge. This is a charge for ensuring basically that there is enough just bulk generation that is built to provide energy. So this you could think of as your variable costs. The commodity is the energy, and the capacity is sort of the fixed cost of building your energy generation equipment. You then have the high voltage transmission, another 10%, about 30% for low voltage distribution, those last few miles to bring it from the high voltage system to your home or facility. And then you have a number of taxes, fees, and regulatory charges, customer charges associated with administration and billing of your account. So this is a pretty typical breakdown on a percentage basis. In Ontario, your breakdown is a lot more lopsided towards the capacity number. And that number, again, is the cost of building your generation. So most of the electricity generated in Ontario comes from nuclear power and hydroelectric power. Those resources like wind and solar are expensive to build, but very, very cheap to run. And as you can see, that energy commodity portion is a much lower component of the bill. And transmission, distribution, and fees are also proportionally lower than most places in the United States, at least in the southern, more populous part of the province. The drivers of these are very time dependent. So the capacity charge, that's based on your system peak across all systems. In Ontario, this is known as global adjustment, which is something I'm sure you're familiar with because it is by far the biggest line item on your bill. Capacity has to be sized to basically the absolute peak amount of load plus a reserve margin to just ensure that there is a safety factor there, that when everyone has all of their equipment on at the same time, there is enough just bulk generation on the system to meet that demand and avoid having rolling blackouts. We had a problem with this in the US and Texas in February that you might have seen when a lot of generation unexpectedly went offline in the winter and set power prices very, very high and had rolling blackouts. So Ontario manages this problem by saying, we're going to forecast load growth and we're going to have people that actually contribute to the peak hours pay for the cost of basically expanding that bank of just generation that is held in reserve on the system. Your distribution and transmission charges, these are mostly recouped via demand charges, and they are based on your individual facilities peak. Your energy costs are variable. So they're the Independent Energy System Operator in Ontario, IESO, publishes an hourly Ontario energy price, the HOEP. That varies hour to hour based on real-time supply and demand. So if it happens to be a very windy day and it's mild, people aren't really running much heating or air conditioning loads, your HOEP price can drop very low. In fact, it's zero a significant part of the year. About 20% of hours, I believe, last year had about a zero HOEP price. So this varies. And on the converse, in July, heat wave, hottest day of the year, that HOEP price can rise significantly to be several $100s per megawatt hour or tens of cents per kilowatt hour, to put it in other terms. So each of these are highly variable. They're dependent on either your individual peak, how your load interacts with the system-wide peak, or the just real-time supply and demand economics of energy. And obviously the fees are fixed. That's the one component that doesn't vary, and it's a very small component of cost. What this means is if we had an electric load that we turned on during that lowest 75, 80% of hours, you'd be looking at what I'd call an off-peak cost. That's about 20 to 25% of the average cost. So your fees would stay the same, your distribution and transmission, assuming you weren't doing anything clever to manage your own individual peak, would stay the same, but your capacity charge, the global adjustment charge for large Class A customers, completely goes away. And your energy charge is also reduced substantially by about 40 or 50%, simply by avoiding those highest cost HOEP hours. And what you're left with is a total all-in cost of power about 20 to 25% of the average cost. And this is how that paradox that I mentioned is solved. You have very, very high average prices because of the costs of building, the legacy costs of building that nuclear and hydroelectric power, but the variable costs of running that equipment is some of the lowest cost power in North America, if you can avoid system peaks and be a well-behaved customer from the utilities perspective. So if there's one thing that I could just teach people about the power sector, and is in our view, there's really actually an overly high amount of emphasis on efficiency, whereas when electricity is used is actually far more important than how efficient something is. So if you have a load, and you might be able, obviously efficiency is important, but if you have a load and you shave a couple percentage points or even double the efficiency of that, okay, you're looking at a 2x decrease in the amount of energy you consume, and that's important, that's good. But as I've just shown, the amount of costs that vary with when you use electricity, instead of changing by a factor of 2, really change by a factor of 100 up to 1,000, depending on when you're using it. So time of use is much more important than how much is used. And this is also true, while I showed it from an economics perspective, this is also true from an emissions perspective. The times when the grid is most constrained, you're using your most carbon intensive resources. So on those hot days of the year in the summer, you might be running oil peaker plants that are burning a very carbon intensive oil and very old, very inefficient plants. And that's also much more carbon intensive to meet load at those peak times. Whereas in the off-peak time, your marginal producer might very well be zero carbon hydroelectric power. And the carbon intensity of the power at that time might be zero. So from both a cost and an environmental standpoint, when electricity is used, much more important than how much is used. That's something that I would just love to teach people about our sector because I think it's very often overlooked. So that's one half of the backdrop of our systems and the opportunity there. The second half is natural gas pricing, and specifically the federal carbon tax increase. So for one, this year with economic recovery underway and just a lot of regulatory changes globally, gas prices, as you know, have been skyrocketing. So this is based off of last year's prices, but beyond just the carbon tax, we're seeing an increase in gas prices. It's anyone's guess where that will go, but what we can say is over the next 8 years, even if gas commodity and delivery prices remain steady, Ontario greenhouse growers will be looking at about a 25% increase in gas costs at minimum over the next 8 years, just due to increases in the carbon tax. Now, due to a lot of the work by OGVG and others, you're shielded from the majority of that carbon price impact. Ontario or agricultural entities are only responsible for 20% of the carbon price increase that's levied on most other industries in Canada. Recently in July, I believe, the federal government announced that that price would be going up $15 a ton per year starting next year from its current price. That'll bring it up to about $170 a ton by 2030. Now, growers, like I said, only have to pay 20% of that as of now, which is great. That makes sense. You guys are very trade exposed. And since us in the US don't have a carbon tax, it would be completely brutal for you all to have to pay that and compete with US growers. So that makes sense. But even here, if the current trend of rising gas commodity costs don't continue, even then you'll be looking at some increase in natural gas costs over the next 8 years. This graph shows trend in delivered prices for in-bridge natural gas, just the variable component, not any fixed components associated with demand charges, but that variable price will increase from about $4. Now it's sitting a bit north of $6 a million BTU, I believe, and it'll go up to about 7.5 over the next 8 years is what we're expecting. So that's the second backdrop I'd like to leave you with. And with that, I'll touch briefly on our solution. So as I mentioned, Medley Thermal, we develop projects that hybridize boiler loads. In the process, we call dynamic electrification. So dynamic electrification, it typically looks like a low-cost retrofit that converts a boiler system into intelligent hybrids. And this allows you to reduce energy costs and reduce emissions. So a dynamic electrification project typically looks like installing a new electric boiler in parallel with a facility's existing combustion boilers. Typically, these are burning natural gas, though they could also be burning any other type of combustible fuel. Our company then provides software that dispatches that electric boiler based on real-time grid conditions as well as facility conditions, basically looking at right now, is this a time when electricity is going to be a lower cost resource than your status quo fuel source? If so, the controller that we provide starts to ramp down the gas boiler and ramp up that electric boiler. We've been developing these projects. We're a US-based company. We've been developing these projects in northeastern US, where fuel costs are very high, as well as in what I call the wind belt of the US that stretches from West Texas up to the Dakotas, and further up into Saskatchewan as well, where a lot of wind energy has been coming online. I was actually just in Texas last week. We're working on a project there up to 50 megawatts of boiler load. They say everything's bigger in Texas, and it's true. It's quite a large project, which is exciting. We recently started working in Ontario as well, despite being a US project. We're working with one producer that's in the greater Toronto area that is processing another type of agricultural product into and started working with them, seeing if there was a fit in Ontario. And as we looked into the Ontario market, what we realized was because of those trends that I just discussed, that real extreme concentration of power and peaks, the backdrop of rising natural gas costs, and the backdrop of a federal carbon price, our offering probably was actually stronger in Ontario than any of the US markets we've traditionally been working in. So just recently, we've started working and beginning development of a number of projects in Ontario. We aren't yet working in the greenhouse sector. That's something that we'd like to explore, and I'll close up with a little bit more about what partnerships in particular we're looking for. A bit about the technology. We are not electric boiler manufacturers or providers. We don't rep for any specific manufacturer. We provide project development and software services, and we help each project basically find the right hardware to solve their specific needs. So we are hardware agnostic. We're basically looking for the best solution for your facility. But electric boilers are manufactured by a number of different brands. Cleaver Brooks is particularly well known. Two large European-based producers, Alpina Technic and Perrot, they're Swedish and Norwegian companies, respectively. Obviously, they're very much like Quebec, very high concentrations of hydroelectric power. They've been doing electrification of thermal loads far longer than other places because they've had just abundant, very cheap electricity, similar to Quebec for quite a while. Then Vapor Power is another US manufacturer that specializes particularly in electric boilers. Just to give you a sense for what this equipment looks like, for most greenhouses, you would be using the larger high voltage boilers. These connect directly at primary distribution voltages, which reduce costs of transformation and reduce power costs even further. But they look like that picture there on the right. It's indicative really of all the major manufacturers. The cylinder, probably 5 to 6 feet in diameter, and then 10 to 14 feet tall, depending on the capacity of the boiler you're looking at. These come in sizes, to put it in boiler horsepower equivalent. You can get these up to 5,000 boiler horsepower if I'm doing the conversion right on the fly. Very large. And then of course, if you somehow needed more than that, you can bank multiple ones together to get that capacity. They're also very flexible. So this equipment is typically used outside of the places where there's just abundant cheap electricity. They're typically used as emergency backup systems for gas-fired systems. So we see them. I'm not sure about the CANDU reactors in Canada, but my background is nuclear engineering here in the US. I know in a lot of US reactors, they will have these electric boilers to help heat up the nuclear power plants and run systems there, especially during startup, or if there's a situation where there's an issue elsewhere in the nuclear power plant. And they're used there because they're highly reliable and very, very fast in being able to ramp up and down, which is useful for our purpose as well. If you happen to run a smaller site, you might be looking at a low voltage boiler, which just that's basically a little bit less sophisticated piece of equipment. It's basically an electric kettle. It has resistive heating elements in a box, probably 6 feet on a side, looking like a cube. That's the low voltage unit, but pound for pound, much more compact than a traditional gas-fired unit. Also, no local emissions that you have to deal with, so a little bit easier to site. You don't need any, don't have to do any flue gas management or real environmental impact permitting. As I mentioned, we've been looking at starting development of other projects in Ontario. Typical benefit for an Ontario facility is we see a net reduction in boiler energy costs of 25 to 40% by installing the system, and electrification of 60 to 80% of the thermal load. Because your grid in Ontario is very, very clean, that's almost a 60 to 80% reduction in emissions. And typical return on investment is a 4-year payback period. Now, I want to caveat that every sector is unique, and we've recently started talking to the folks at OGVG. Your sector is even more special and unique. There are a lot of things that we are aware of that make how you use energy different, which will mean that these numbers may not translate to your sites at all. We're completely transparent. We're new to working in this industry. We want to explore whether there is a fit for this type of solution in this sector, and the answer very well may be no, and I'm open to that. But this is what we've been seeing for other industries in Ontario that have significant boiler loads. I just want to make sure that I've fully caveated here that we can't yet say that this is what we expect to see for any specific farm. Beyond that, I know a lot of the facilities we're working with are concerned about basically locking in the role of their combustion boiler. And I want to highlight that there is a pathway here to net zero if that is something you are concerned about. So in our view, phase one is this dynamic electrification with your existing fossil fuel boiler. There's still opportunity to, whenever technology develops or regulatory pressures or customer demand warrants it, to swap out that fossil fuel combustion leg with any other sort of zero carbon backup system. We're working on a project in Maine right now that actually has already gone completely biomass. They've decarbonized, but dipping into power is still a way for them to save money while not compromising on that net zero goal they've already achieved. So you can always, as a second phase of that project, take out that natural gas leg and replace it with something like a drop-in replacement for renewable natural gas, biomass, biofuel, hydrogen, or, and what I think would probably be best for growers is some type of thermal storage, some sort of tank to store hot water or steam for when you need it, and use that to avoid electrifying at those high cost times. What's also nice is these stored zero carbon backup systems tend to cost more to operate than direct electrification during the off peak or just burning natural gas. So you're concentrating in the fewer and fewer hours how often you'd have to use that more expensive resource of a stored zero carbon energy source. Another benefit that we've started to uncover as we've been talking about this with OGVG and others is for smaller growers that currently don't have a Class A designation, these projects can help qualify for that designation. So typically a Class A power consumer pays about 35% less than a Class B power consumer. This is probably potentially even more true for greenhouses because your load profile does not follow the typical load profile in Ontario. So when you're peaking your electric loads, it's very unlikely to be the time that the system-wide is peaking. So that benefit might be even greater for growers. It's something we'd be interested in looking into with some of the growers here. Obviously, a big concern is adding this amount of load can be difficult, particularly in the Leamington-Kingsville area. We're aware of that. We've already been having preliminary discussions with the IESO and local utilities about a pathway to make essentially exceptions for load growth as long as that load growth is curtailable. And what I mean by that is even though there are issues getting new firm capacity in the region, there's still the majority of the time plenty of excess capacity. And as long as the utility had an assurance or a guarantee that these new electric loads could be turned off at times when there is a local transmission or distribution constraint, the majority of the time there would not be an issue to adding that load on the system. And of course, with our hybrid systems that we provide, we could easily loop in a signal from the local utility or the IESO to back off on the electric consumption and ramp up the gas consumption during any of those constrained periods and include that in the optimization. As I mentioned, we've already been exploring that with the IESO and the utility. We're working with a few utilities in the United States on a similar program. And what we've seen in those networks is even places where you have a capacity constraint for delivery, most of the time you could actually double the amount of load on the network and be fine. You just need that assurance that that extra load isn't going to contribute to the peak and cause a reliability issue. Just jumping back to our company and the services we provide, again, as I mentioned, we're not a boiler manufacturer or rep. We provide two services. We do the development, so we can take as much or a little role there as a customer would like. We can provide economic assessments of what the project would look like. We can provide engineering services. We can help set up electricity supply contracts, so you have forward certainty that you're going to get a rate of return on this investment if it's something that you are interested in. We can also provide financing for that project. We've been working with a few institutions within Ontario that are interested in providing financing for these types of projects within the province specifically, as well as a number of just larger institutions that are geography agnostic. And then secondly, we provide software solutions that dispatch that hybrid system in response to those real-time market considerations. As a bit of background on the software, we have a software platform that responds to market prices and forecasts. So we're looking in real time at that HOAT price, as well as providing short-term forecasts. The load is very flexible between the gas and electric boilers, but not infinitely so. And we obviously avoid overly ramping or cycling the gas boiler. So we incorporate forecasts into the dispatching decisions to ensure that we aren't overly taxing the flexibility of the gas boilers. As I mentioned, the emissions of the grid are also highly variable over time. Some of our customers have asked us to incorporate grid emissions, real-time grid emissions, into the dispatching consideration. So basically including a shadow carbon price that is factored in and looking at how that real-time mix of energy resources is changing and incorporating that into the dispatch decision. Beyond those commodity prices, obviously there's delivery costs. So we look at tariffs and contracts. We can help manage demand charges as well. So for example, if you are a lit facility that has a large lighting load, we can build forecasts of your lighting load and incorporate that with a dispatch of the electric boiler to help minimize demand charges. So if you're already incurring a demand charge half the day for lighting, you're already paying basically for that capacity to be, that wire to flow power to your plant. Makes it much less expensive to run that electric boiler if you're already basically paid for that demand charge for the lighting, and we can basically fill up the times when the lights are off with the the electric boiler during that month to get a even lower cost. And then of course the technological constraints of the system. So both boilers, particularly the electric, are highly flexible, but not infinitely so. So we can incorporate a number of other technological constraints. One that we would be looking at as well is obviously potentially looping in humidity monitoring and control systems as well, and understanding how for your industry that impacts dispatching decisions as well. And as I alluded to, we can provide financing through a number of local and larger institutional partners. Typically, this takes the form of a steam purchase agreement. If you use hot water, it can be just any sort of energy purchase agreement. But under these agreements, they work very similarly to a power purchase agreement that you might be familiar with if you've looked at developing, say, on-site solar or other types of services. But under a energy purchase agreement, essentially a financier would pay the upfront cost of the retrofit, and the savings of that project would cover the cost of the financing and the software, as well as giving you some small immediate savings. Then after the financing term and you've paid out the system to the financier, the savings increase to you. So if you look at this graph at the bottom, this gray block is say your current energy cost. After you install the equipment during the agreement, that energy cost drops somewhat initially. So you're seeing savings day one without having to put any capital forward. You're paying off this orange block, which is the financing. We make our money through a software fee, which is small that we charge, and your energy costs are much lower. After you've paid out of that steam purchase agreement, the financing cost drops off, and there's an increase in the savings for the end user. Of course, we're not in this to make money on the financing. We see that as a tool to help facilitate projects. If this is something that meets your capital budgeting cycle and rate of return, we're more than happy to just help you develop the project without financing and provide software services. We're agnostic to providing financing, and if you have your own funding you'd like to bring to that, we're happy to work with them as well. So lastly, I'd like to just go through a case study. As I mentioned, we are new to the greenhouse market, so I don't have a greenhouse case study for you. That's something that we'd love to develop and pencil out with a grower that was interested in exploring this. But I can provide a study for Jay Peak. This is a ski resort, actually about 5 miles from the Canadian border in northern Vermont. I picked it as a case study because the economics are pretty similar to what we're seeing for the projects under development in Ontario, and also their load profile is fairly similar to what we're seeing for growers. You have demand throughout the year for heating, but there's obviously a seasonality to it, and they use much more in the winter and shoulder seasons than in the summer. So this project currently being installed has a propane spend of about $1.1 million US a year, burning that propane to heat their I didn't mention what they use the heat for. It's actually kind of fun. As you can see in the background here, they have a large indoor water park. Part of the strategic plan for the resort was moving to being a 4-season resort, making sure that they can utilize the assets that they already have in terms of a world-class hotel and conference center, use that year round as opposed to just the skiing season. So a few years back, they built this quite nice indoor water park. It's very pretty. As you can see, there's that glass ceiling, which is really nice. You see the mountain in the background, but obviously a little harder to heat. So they have quite a large heating expenditure for the water park and hotel and snow melt systems. And they have about a propane spend in their boilers, about $1.1 million. Burning that emits about 4,000 tons of CO2 a year. So if you look at this little stylized chart I have, their propane cost over a heating season is pretty flat. It might be changing on a month-to-month basis, but compared to electricity, which changes hourly, it's essentially a flat cost. Behind that, they have a power price with their utility, Vermont Electric Co-op, that is changing hour to hour. Once we've installed the electric boiler, we're projecting electrifying, I believe, 75 to 80% of the load. So that's the new spending of the resort will be $280,000 a year on propane, $600,000 on electricity, leading to a net savings of about $220,000 per year and a 2.6 thousand ton of CO2 annual reduction in emissions. So that's 75% electrification and a 20% overall cost savings. We're expecting the project, we've received bids, we're expecting it to come in actually a little bit south of that $850,000 number, and a 4-year payback is what we're anticipating there. And that's before any subsidies. The project actually qualifies for a few state level incentives related to the emissions reduction. So the resort will actually be doing quite a bit better than that with the money that they're putting forward. But with that, my ask to you, as I've said, we have been working historically in the US. About a year ago, started deciding to focus more on the Ontario market because we believe there's actually greater alignment between the projects we offer and the Ontario market. We've been working with a number of different industries in Ontario, but not greenhouse growers to date. We see that there could be some opportunity there, but there's also quite a few distinct challenges for greenhouses that we're already aware of. And I'm sure that there are others that we would become aware of as we started looking at partnership opportunities. One is obviously, we know many of you reuse the CO2 from combustion. So understanding that dynamic and how electrification of part of your load would affect that dynamic is obviously something that we still want to do some learning on, and we'd love to work with the grower to help explore that problem. The interplay between heating and humidity concerns is a second one. We know we'd have to update our software to account for that specifically. And as we are all aware, there's just a problem getting power to the region. As I mentioned, we've had some preliminary conversations with the local authorities about exploring opportunities to allow new load growth, as long as there is a mechanism for the utility or the IESO to say, okay, we need you to back off on the electric boiler and go back to the gas boiler. So we see a path forward on each of these, but I want to be frank, we don't have a fully packaged product ready to go. What we're really looking for here is a partnership opportunity for someone who might be interested in piloting this project that we're already developing elsewhere and deploying elsewhere for a different industry. The first step of that would probably be a data exchange, just assess high-level cost benefit, diving in more to these distinct challenges to deploying this project in the greenhouse sector. But to help mitigate that, there are a number of IESO and government grant opportunities that we're already looking at that could help us deploy early projects in the sector. And if someone was interested in partnering with them, we'd be happy to help draft that application to the relevant grant agency and apply for funding to either explore or ultimately deploy one of these projects at a greenhouse. So with that is really all I have for you today. Thank you again for your time. I'd be happy to take any questions.
Thanks, Jordan, again for putting that together and for giving us a bit of an introduction on this. I did get a couple questions in the group, in the chat as you were going. So the first is, what is the minimum size in acres to make sure we use enough electricity to get Class A?
The minimum size in acres. Honestly, we have just started speaking with a smaller grower that's about 5 acres, and that would still hit Class A. These things take a lot of power, which is good and create some challenges. Typically, the largest cost of the project is the upgrade to the electricity system that needs to be made. but most greenhouses that are 5 acres or above under roof should be enough to get Class A.
All right. And next is, can software account for CO2 demand from CO2 boilers during the day?
It's not something that we do now, but we would be happy to develop that as a feature to make this a fit for your greenhouse. And that's not at all atypical. Other industries we work with have their own unique needs that we have to account for in the optimization. So as long as we can define that with a grower and say, okay, we have a CO2 monitor, and that means we need to be running the gas boiler at minimum this much to hit this ppm of CO2. That's not something that we do, but it's honestly not a huge step for us to do that. It's very similar to other constraints that we have to include for other industries.
Another question is, most greenhouses now use hot water. Can the
Yep.
software use tanks and CO2 demand during the day?
Yes. So I know a lot of greenhouses have shifted to having hot water tanks, and that honestly makes the value proposition much stronger because it's basically a thermal battery for you. And we've been looking at other projects to incorporate thermal batteries as well, because what essentially that lets you do is concentrate your charging of your system and even lower cost times. And it also makes it easier to mitigate the demand charge. So your distribution and transmission charges would decrease if we're able to incorporate that intelligently. So yes to both. We're able to, for each project we work with, there is software adaptation. Each facility is different. That's part of our development process. And working with thermal batteries is something that we are already doing. So that's something that we could do with a hot water storage tank.
Would you expect operation costs to increase if, say, multiple farms start running these electric boilers at the same time?
The costs of electricity. I mean, what the price for load in Ontario is set Ontario wide. So, and I know that you guys consume a lot of energy. So, I mean, at a certain point, if every greenhouse in Leamington fully electrified, eventually you'll start having an impact, but you have to keep in mind that the price is set by Ontario-wide supply and demand. So it's less of a local effect that's going to drive that. It's only if all these boilers really started to become a substantial percentage of the Ontario-wide load, that would start changing the cost structure. I'd have to look at how much acreage it would take to become a significant percentage of Ontario-wide load. And well, one benefit though to that I didn't mention, one reason that IESO is interested in this is, as I mentioned, most of the time, even though you're constrained, there is spare capacity at most hours. And if the utility and the IESO basically can sell more power during those times when they already have infrastructure in the ground, that fills their coffers and makes it easier for them to spend money on transmission enhancements, distribution enhancements without increasing costs locally. So this should actually have a downward pressure on local distribution and transmission costs because you're using the wires more efficiently. You're basically flowing more power through the same wires that you have. And then from the energy commodity standpoint, it would take a lot of growers jumping onto this to be significant from an Ontario, provincial wide standpoint.
How does electric boilers at COP of 0.99 compare to a heat pump at COP of, say, 1.7?
Yes, so this is something that we've looked at. I would say if you can get a heat pump that meets your temperature differential needs, so on the coldest days of the year, can get you a hot enough water supply to heat your greenhouse adequately, obviously that efficiency gain is important. So we prefer the electric boilers, but we'd be happy to look at a project that use heat pumps. What we would look for is how flexible that is and whether that can meet your need during the coldest day of the year. As I mentioned, we are hardware agnostic. We've used electric boilers. We're working on a number of projects that don't use boilers but use other types of electric to heat elements for hot oil systems or other things. So we are hardware agnostic. What's most important though is having a flexible system. So we'd have to look at how flexible that heat pump could be. As I mentioned, if you have a 99% efficient electric boiler, so COP of 0.99 versus call it 2 in an ideal case. It's a factor of 2 increase in efficiency. That's obviously very important, but our view is being able to avoid global adjustment, being able to avoid high HOAP hours, being able to manage the demand charge by being smart about when you turn on relative to other greenhouse loads is far more important than that 2x efficiency increase, and will actually get you a lower cost and then lower emissions than using the more efficient heat pump. But again, hardware agnostic, so we'd be happy to look into it if that would meet your needs. For many of the projects we work on, they're using steam, so a heat pump is just out of the question because you're not going to be able to hit the temperature that you need with that type of equipment.
Could the electric boilers work off either steam or hot water?
For a single site, or well, I can answer both. If your site needs both steam and hot water, we can add a step down that basically produces steam and then steps it down to hot water. But yes, if your site only needs one or the other, we can provide one or the other. No issue. Electric boilers are configured for both.
How does your boiler compare with a gas boiler in reference to BTU and kilowatt hours? I'm not sure if you said that earlier.
So BTU and kilowatt hour, one megawatt hour is about 3.41 million BTU. So that's the conversion between them. These things get big. So if you have, they make electric boilers that are extremely large. So 50 megawatts would be 150 million BTU an hour, if I'm doing the math right off the top of my head, which is always dangerous. And again, if you needed more than that, you could stack them together, and they go as small as you want. So they have units that are designed for households and everything in between. So that's one of the reasons why we're hardware agnostic. Different manufacturers specialize at different size ranges and have better product offerings, in our opinion. So we can help guide you to the right manufacturer. But these things are, the biggest applications, they use them in China to provide district heating for mega cities of 10 million plus people. And they use them in individual households and apartments, and everything in between is in play. So size is not really a limiting factor from the boiler perspective.
So what is the life expectancy of an electric boiler?
For a high voltage electrode boiler, I always say 30 years. We've asked the manufacturers of these. These have been around for almost 100 years. The Norwegian manufacturer says they have original ones that have been in place for 70 years. The maintenance on them is pretty low. Every 7 to 10 years, you need to replace the electrodes, which is low tens of thousands of dollars piece of maintenance that has to be done, probably 10 to 20. With steel going up, maybe it had a little bit more than that every 7 to 10 years, but they're much simpler than combustion. There's no fouling because you're not burning anything. The heat transients are actually a lot less because the way they're configured, the water actually isn't in direct contact with the steel, and that leads to just less creep and fatigue on the pressure vessel, even though they are very flexible. So they last at least 30 years, realistically 50 plus years. And as I said, the manufacturer still has some of their earliest ones in operation, and they can't say because it's been kicking for 70 years and it's still going strong.
Do you have a comparison of electric and gas boilers in BTU to meters cubed natural gas and BTU kilowatt hours electricity?
Yes, but I can't do that live.
Okay.
So I can, if someone is interested in this, I can give you all the units between BTU, KW, boiler horsepower, cubic meter. What's interesting about this is we are working in 2 different sectors that typically don't talk the same way. So the units are different, and it's always hard to think in the units that aren't natural for heating or for electric. So that is a bit of a challenge, but I can provide that to anyone that's interested after the call.
Yeah, for sure. Just send it over to me and I can
I'll do that. Yeah.
Forward it over. So I have one more question here. What are the specifics for how much cleaner it will be, like going electric?
So I can provide a bit of info on that. As I mentioned, in addition to cost varying throughout, hour to hour, emissions factors also vary hour to hour. So about 30% of the time, we can show that the marginal emission, which basically means how much more CO2 is going to be emitted to serve your load, is actually zero in Ontario. And then that starts to go up as you get to higher numbers. So as I mentioned, these peaks, which also coincide with the high cost times, are the most emissions intensive. Now, if you're electrifying 75, 80% of the time, you do cut off these peaks. So you're doing a little bit better than average. Currently in Ontario, we've looked at the carbon intensity. This is so this is basically saying you're going to run 80% of the time. A natural gas boiler, you're emitting about 225 kilograms of CO2 per unit energy. And then for a dispatched electric boiler, it's less than 10% of that. To 20s, low 20s kilograms of CO2 per unit energy. What's interesting is that's also lower than a biomass boiler, if that's something you're interested in. It obviously depends, but the emissions from the biomass come because most of that biomass in Ontario is being transported from the more northern part of the province by truck to the loads in the southern part of the province. When you account for the emissions intensity of the transportation, it's actually a little bit more carbon intensive than the dispatched electric boiler. So if you're looking at, say, 80% electrification and your electricity is 10% the carbon intensity of the gas, that ends up being 90% times 80%. So 72% reduction in emissions is what you'd be looking for after you account for the emissions intensity of the electricity. And again, if you're using that CO2, we can include that as a constraint and say, okay, we're not going to electrify as much because we actually are going to reuse some of that CO2. And that's not an issue. And we can project what your emissions reductions will be for that as well.
So does an electric boiler require a 24/7 on-site stationary engineer?
That is an excellent question. It varies state by state and province by province. In most places in the US, the answer is no, because it is an unfired steam generator. There's a lot less that can go wrong. But if you have with what we're proposing, if you have a gas boiler as your backup, you're going to have that anyways, and the same person in every state that we've been working in can serve as both. If you have a thermal hot water tank and don't need a backup system because you have that storage system and you could go 100% electric, we'd have to look into that in more detail. That's something that I'd have to take and do some research on, to be honest. I can say it's a state issue in the US, and in most cases the answer is no, but not every state.
All right, and that's all the questions that I have in the chat right now. But if anyone has any further questions proceeding this call or would like to know more about dynamic electrification, please reach out to myself or Jordan. Thanks again, Jordan, for today.
Thank you all for taking the time. I appreciate it.
Yeah, for sure. So I hope everyone has a good rest of your day, and we'll talk soon. Thanks.
Thank you, Sierra.
Bye.